So hi everyone. In the last video, what happened was we sort of described three types of cost functions, namely the total cost function, the average cost function, and the marginal cost function. And what we're gonna do in this video and in the subsequent video will be we're gonna try to graph these functions given different conditions or cases, and we'll see some interactions between these functions. And I think it's much easier to see these interactions graphically than just merely doing the math. So let's start. The cost curves, okay, which is essentially the graph for a cost, okay, is drawn under the assumption that, for now at least, that input prices and the level of technology are held constant. As such, any change, okay, in these factors will cause cost curves to shift. That is, go up or down. Okay, and the magnitude or the size of these shifts, okay, will be determined by the importance of an input and the substitution abilities of the firm. Okay, so that happens when there's a change in the level of technology and input prices. But again, in this case, we're gonna assume that they're held constant. Okay, now we're gonna explore three different cases among the interactions of total cost, marginal cost, and average cost. And that's when the firm has constant returns to scale, increasing returns to scale, and decreasing returns to scale. So we'll start with constant returns to scale because this is where the example that we answered in the last video was leading us up to. Okay, so if you recall, okay, earlier we had the production function L raised to 0.5, K raised to 0.5, and we derived the conditional demand functions, which is for L and K here. And then, uh, so for example, we want to get the total cost function. So the total cost function, or just C rather, so C, WRQ, is just determined by substituting the conditional demand functions to the cost function. So you have W times R over W raised to 0.5 times Q, plus you have R times, so K is W over R raised to 0.5 Q. And what's gonna happen here is you're gonna have W W raised to 0.5 R raised to 0.5 times Q, plus same thing here, you have W 0.5 R 0.5 times Q, and you're gonna be left with 2 W R raised to 0.5 times Q. Okay, and this is your total cost function. Now, okay, what we want to prove is that, what we want to say is when the production function has constant returns to scale or exhibits constant returns to scale, okay, that is, if I increase the inputs by some proportion, the output will also increase by that same proportion. What we'll notice that is that when constant returns to scale is exhibited, the total cost function is linear in output. What does that mean? Well, it means that total cost, okay, increases with output at a constant rate as well, with input prices held constant, of course. So again, total costs increase with output at a constant rate. Okay, now, and you can visualize that graphically, something like this. So under constant returns to scale, C, okay, your cost function is linear. So that's C. And when the function has constant returns to scale, okay, we can see that, so for look at the curve here, the slope of the cost curve, okay, that slope, okay, is essentially the marginal cost, right? So this is the slope, that's marginal cost. Then it must be that since C, your total cost, your cost curve, is perfectly linear, then it must mean that marginal cost, okay, or the slope of that, is as well constant because it's a linear graph. And it's linear in Q, so it's linear with output. And what we'll notice is that when there's constant returns to scale, okay, average cost and marginal cost will be constant. It will be constant because we have a linear cost curve. Okay, and we can prove that mathematically. So we have our total cost function here. What we can do is we can derive, okay, we can derive the average cost function and the marginal cost function. So if you derive the marginal cost function first, so MC, that's just equal to partial of the total cost function with respect to Q. So this one will be, we can just use a simple product rule. Derivative of this with respect to Q, that's just 2 WR raised to 0.5. And average cost is just cost over Q, so that's just 2 WR raised to 0.5 Q over Q. You get 2 WR 0.5. And you'll notice that average cost and marginal cost are equal. And both of the unit costs are constant. So for example, say we have R and W being equal to 4. Again, this is exogenous to the firm. They have no control over that. Okay, we can say that if you plug that in, you'll see that if you plug in 4 and 4 here, this is going to be equal to 8. And this is also going to be equal to 8. Okay, so in this example, when input costs are there, average cost and marginal cost are equal. Okay, now, so that's constant returns to scale. Now, we're gonna see a different example. Okay, when the firm displays or exhibits increasing returns to scale. So let's go to increasing returns to scale. So with increasing returns to scale, the total cost function is strictly concave in output. Okay, and what does that mean? It means that if the cost function is strictly concave in output, it suggests that total costs increases with output at a decreasing rate. Because at the start, you'll notice since it's strictly concave in output, okay, so we have here, so there. So this is how our cost function or our cost curve would look like. So notice as C increases, okay, as C increases, so again, marginal cost is the slope of this graph here. So as C increases, what you'll notice is that the slope, okay, decreases and decreases as the amount of quantity or the output produced increases. Okay, so it suggests that total cost increases with output, but it increases at a decreasing rate. This implies that the second order derivative of the cost function with respect to output is negative because it grows at a decreasing rate. Okay, so you'll notice that MC, or your marginal cost, which is that slope there, decreases as Q is increased. Okay, so in this case, we can also show that AC also decreases as Q increases, but you'll notice that average cost is greater than marginal cost for all cases in Q. Okay, so if we try and graph MC and AC, they look something like this. Under increasing returns to scale, so you're gonna notice that AC looks like that, and MC looks something like that. If we just graph it in another graph. Okay, so what you'll notice is that AC is greater than MC if you try and manipulate certain things, and that's how it's gonna look like under increasing returns to scale. If you want to try a function with that example, you can opt to try Q is equal to FLK is equal to L squared K squared. So this function is a production function that displays increasing returns to scale. Now, for the last example, we're going to have a function that displays decreasing returns to scale. Decreasing returns to scale. And that's when the total cost function under decreasing returns to scale is strictly convex in output. Okay, what does that mean? If this function is strictly convex, it means that total cost, okay, increases with output at an increasing rate. So sort of like the opposite of increasing returns to scale as expected. So the cost curve looks something like this. Okay, so we have, say, cost. Okay, and that's a strictly convex graph. Okay, so what you'll notice is, again, doing that slope example, the slope initially is kind of flat but gets steeper and steeper as q is increased. Okay, and this implies that the second order derivative, okay, is positive because cost is increasing at an increasing rate. Okay, so it implies that marginal cost is also increasing. Since the slope is increasing, marginal cost increases as q increases, and so does average cost. But this time, okay, what you'll notice is that marginal cost is greater than average costs. And if we're going to graph this one, okay, it's gonna look something like this. So we have, say this is marginal cost, and this is average cost. Okay. Now, if you want to explore an example, you can opt to do the similar procedure using this production function. And it's going to be L0.4, K0. So this is an example of a production function that exhibits decreasing returns to scale. So in the next video, we're going to discuss an example wherein we have variable returns to scale, or a cubic cost function. So for now, we have three cases: constant, decreasing, and increasing returns to scale.